In this class, we're going to consider first-order linear differential equations. So first order just means that the equation contains a first derivative. Other types of differential equation will contain higher order derivatives, like a second or a third derivative. It's not always the case that if you've got a first-order linear differential equation that you can solve it by separating the variables. So hopefully you're already familiar with the method of separation of variables. If not, maybe check out that class and then come back in here. So if you try using algebra to separate the variables and it doesn't work, it doesn't mean that the equation's not solvable, it just means you've got to use a different method. And that's going to happen quite often. So you try maybe separating the variables, doesn't work, you're left with something else. But if that something else can be put into a particular format, then you can use another method. And the method we're going to define in this class is something called an integrating factor, which is a really common way to solve first order differential equations. So let's say you've been given an equation. It might already be in the correct format to use the method we're going to look at in this class, or maybe you've tried to separate the variables, or you've done some algebra and it's ended up in this format. But the format we're looking for is that we've got our first derivative, so let's call that dy dx, plus some function of x, let's call that p of x, multiplied to y, equals, on the other side of the equation, some other function of x. So this might just be how the equation already looks, like in the case of this one, because this is just really an introductory type class, and this is just an introductory problem. Or maybe you'll be given a problem where the equation doesn't look exactly in the correct format, but you can manipulate it into the correct format. That's part of the challenge of differential equations in general, is not only getting the format to match the type that you then know how to solve, but sometimes manipulating the equation into that correct format. And that is quite challenging. So let's assume that you've been given an equation and it either matches this format or you can make it into this format. What do we then do from there? Well, we define this thing called the integrating factor. So let me just write down that term. It's a really cool little method, this. It basically transforms the equation. So an integrating factor. And the way that we define this integrating factor is going to seem a little bit strange at first, and I'm not going to show the derivation of this, but the integrating factor is defined as e, as in like the number e, to the power of the integral of this p of x function, so the integral of p of x, and we're going to integrate that obviously dx. So it might look initially like, wow, this looks really complicated and it looks really weird. It does look a little bit weird, but sometimes you'll find, in fact quite often you'll find that when you actually evaluate this, it comes out to be quite compact, quite a concise solution. What we then do with the integrating factor once we've evaluated it is we multiply through the original equation. Multiplying through the equation transforms this original equation into a format that we can then solve. It doesn't make it separable, it doesn't transform it into a separable equation, it transforms it in a way that we can then just solve directly by integration. And it's really that, in the derivation of why that works, that's why we define the integrating factor this way. But let's not worry about the derivation, let's just focus on the practical sort of use of this technique. So with any differential equation, we're always trying to sort of pattern match. We're trying to determine, hey, what type of equation have we got here? Is it in the correct format? So if we look at our example problem here, we've got the first derivative on its own, and that's really important because if we had, for example, a 2 here, then it might be tempting to say, okay, we've got our derivative and then we've got this kind of term multiplied to the y, so that seems to kind of match up here. And we've got an x function over here, so it seems to be all good. But if that was the case, because the dy dx should be completely on its own, if there was, say, a 2 here, we would need to divide through the equation by 2, which would then change this p of x function. Now, in this case, the p of x function doesn't have an x, but that's okay, it can be a constant function. So just be careful, because if you don't have the format exactly in this pattern here, then that's going to determine how your p of x comes out. So you've got to get the correct format to get the correct p of x to then get the correct integrating factor. If you don't get that, the whole method will collapse. Okay, so just to kind of be explicit about this, you can, if you wish, do this. So I'm going to say here that we're defining our p of x, which is the thing, remember, that's multiplying to the y term. And notice that this y term has to be a y term, not a y squared or a y cubed, just a y. the thing multiplying to that y is minus 4. That's our p of x function, even though it doesn't contain an x. A lot of the time it will contain an x. It's fine for it to be a constant function. And here we can see that our q of x, which we don't really need in the working, but just to define it, is e to the x. So basically, we do have the correct format. So we're going to go ahead then and define our integrating factor. So that's going to be e to the integral, e to the power of the integral of minus 4 dx, and you can just go ahead and evaluate that. And how you evaluate that will obviously depend upon the integral here or upon the integrand. This one's quite straightforward, so we get e to the power of negative 4x, and that gives us our integrating factor. Notice that in these, or note in these, you do not need a plus c. We're going to work more examples of these in the next class. This is really just an introductory example. So once you've got your integrating factor defined, and if you want to, you might need to fully simplify here or something, I'm happy to leave it in that form. We can then multiply through the equation. So literally just multiplying every term by the integrating factor. So we're going to get e to the minus 4x multiplied to dy dx. Then I'm going to multiply to this term here, so we're going to get minus 4, I'm going to go with the e term first, so minus 4 e to the minus 4x multiplied to y, and then we're going to get e to the x multiplied to e to the minus 4x, which we can tidy up in a moment. So let me just go ahead and work on the right hand side first of all. I'll just quickly tidy that up. So these have got the same base, so we can use our exponent rules just to combine the two powers. Remember, this is like a 1x in here, so we're effectively going to get e to the power of 1x minus 4x, which is e to the minus 3x. But the important thing with these type of differential equation, these where we're going to use the integrating factor, is that the left-hand side, which probably looks really messy now, it probably looks a lot worse than when we started, the left-hand side can now be defined, and I'll explain this in a moment, but it can now be defined as the derivative with respect to x of the integrating factor, which was e to the minus 4x multiplied to y. And that is another way to write the left-hand side. Let me explain that in a moment. The right-hand side is then e to the minus 3x. Now, notice that this is a product here. That means that if we wanted to take the derivative with respect to x, we would need to use the product rule. So what would that look like? Well, if we take the product rule says to take the first term, multiply that to the derivative of the second. So the first would be e to the minus 4x multiplied to the derivative of the second, which would be dy dx. So that gives us this term here. And then we would add to that, using the product rule, the derivative of the first, which is minus 4 e to the minus 4x. That's how you take the derivative of an exponential function, multiplied to the other term, which is y, which is this term here. So in other words, using the product rule to differentiate this here, we would get this. So this and this are the same thing. Notice also though, what we've got here is, let me just write over here, is the derivative with respect to x of our integrating factor, so let me just call that, say, the if, and the integrating factor, multiplied to y. And that's always going to happen, okay? So at first, these seem a little complicated. This looks very ugly. We're dealing with product rules, like where's this all coming from? But you can just remember that this line here should always just be the derivative with respect to x of your integrating factor multiplied to y. If that's not the case, something's gone wrong already somewhere in the question. So that's the beauty of the integrating factor. Once you multiply through the equation, the right-hand side takes care of itself. The left-hand side is always in this format. That's why the integrating factor is designed like that. That's why we define it this way. It always makes this happen by magic. So that then leaves us an equation which we can now solve. And you might still think, well, how do we go about solving that? It's not separable. What are we going to do? Well, we can just integrate both sides. So if we just basically say that we're going to integrate this side and integrate that side. So I guess we could actually just put in the integral symbol here. So the integral of the derivative with respect to x of e to the minus 4x multiplied to y, and we'll be integrating that with respect to x, is equal to the integral of e to the minus 3x dx. We sometimes skip out this line. You'll find that once you start working these problems, it can get a little bit messy. That's maybe over formalized to put in that line. Basically what we sometimes do instead is we know that if we integrate something that we're differentiating, they obviously are inverse operations and they just cancel each other out. So when you integrate this derivative with respect to x term, it just cancels this bit out and you're just left with inside the bracket. So sometimes we don't write this line of work and we just go straight to the next line, which would be e to the minus 4x y, and that's going to be equal to, and then you could write in your integral symbol. In other words, you could write this in here or put in this line of work in. That's partially your own personal preference. Is a bit of a stylistic thing. You'll see what I mean once you start working the problems. So anyway, we've integrated this derivative, so that's just cancelled those out to give us this bit. The integral here, again, if you've not worked integrals for a while, you might need to review some of your integration rules, but the way that this one basically works is that this would come out to be minus 1 over 3 e to the minus 3x, and then we've got our constant on the end. Review that if you're not sure, but basically if you imagine now differentiating that, it should take you back to here. Remember, if you integrate something, the solution you get, if you then differentiate, should go back to where you started. And the derivative rule for an exponential function is that you take the derivative of the power, this is a chain rule, which in this case would be minus 3, and you multiply that to the original function. So if we take minus 3 and multiply to this, that would cancel out this here to give us what is effectively a 1 in there. So that might take a little bit of practice, a little bit of review. I'm sure you've done those in the past. That's from Calculus 2. So how close are we now to solving? Well, remember, we are trying to write our solution, so y to be equal to some function of x. That's the solution for our differential equation. We can do that just by dividing through by the e to the minus 4x term. So we're going to end up here with y equals minus 1/3 e to the minus 3x. Different ways to write this, but I'm just going to go over e to the minus 4x plus c over e to the minus 4x. We could tidy that up because these terms obviously have got the same base, so we can combine them. So subtracting the power, so it's going to be e to the power of minus 3x minus 4x, which will be plus 4x. That's just basically going to end up being an e to the positive 1x, or an e to the x. The minus 1/3 will stay in front, so we get minus 1/3 e to the 1x. What do we do with this guy? Well, we could leave it in that form. It's a little bit weird, I know, having like a c connected to an x term, but that happens quite often in these. I'm just going to get rid of the negative power by bringing it to the top of the fraction, and it's going to become c e to the minus, e to the, well, I'll make a plus, e to the plus 4x, like that. And that is your final solution. Remember, this is the general solution because we've still got our c in here, our constant of integration. So that's just a bit of an overview and an introduction to this method of using the integrating factor for solving a first order linear differential equation. It does look very messy at first, but we'll work a couple more examples in the next class, and you'll find that this method is very neat and tidy and concise actually. It doesn't really vary very much. It's just kind of getting used to this little bit of algebra in the middle. Just getting used to the method. Like all the methods of differential equations, they're all different. They all vary. You just got to get comfortable with the method. But again, I will emphasize that it's all about the original format. If your equation does not look like this, you cannot use this method. You either need to manipulate it, so it does look like this, and then you can use this method, or it's not that type of differential equation. You've got to use some other method to solve it. So hopefully that makes sense. Try and absorb this technique and the things you need to know, and then move into the next class when you're ready. And we're going to look at a couple more examples of this technique in that class.